Welcome back, everyone. Let's go through another example of an independent samples t-test. We've already gone through example 1, where we found statistically significant results using an alpha of 0.01 and a two-tailed test. And then we also went through example 2, where we found statistically significant results using an alpha of 0.05 and a two-tailed test. Let's see what happens with example 3. What I recommend that you do is stop the video right now and work it out on your own. What makes that example unique is that I don't compute any basic descriptive statistics for you. So you're going to need to compute the mean and sum of squares on your own. Now that's no big deal. I mean, we're computing independent samples t-tests at this point. Computing a mean and sum of squares should be child's play for you. But prove it to yourself that you can do it. Work it out on your own first, and then come back to this video, and then you can compare your answers with mine. At this point, I'm assuming you've already worked out example 3. So I'm going to go through the steps and I'm going to explain them, but I'm assuming you've already done the hard work on your own. Previous research has found that elderly people who own pets are less likely than elderly people who do not own pets to visit their physician after upsetting events. And here we're talking about some type of emotionally upsetting event. Based on the sample data below, are there significant differences between dog owners and control subjects? The control subjects don't have any pets. So we're essentially testing to see if owning a pet, specifically a dog in this case, serves as an effective social support system for these elderly people. This at least somewhat coincides with a medical example, so let's use an alpha of 0.01 and a two-tailed test. We can see that we don't have any basic descriptive statistics computed at all. So eventually we're going to have to start from the very beginning. We'll have to compute means for each group and sum of squares for each group, just to see what the average scores are and the variability. Here's our raw data. We'll consider the dog owners to be group 1 and the control group to be group 2. It's really completely arbitrary which is group 1 and which is group 2. Let's state our hypotheses in step 1. Remember, we have two competing hypotheses, a null and an alternative. The null hypothesis always states in some form that there's no effect. And in this case, what that means is no differences between the two populations. So the way I would write it is that the population mean visits to the doctor for the dog owners. When you then subtract the population mean visits from the control group equals 0. If the difference between those populations is 0, that means there's no difference between the two groups. In other words, they're equal in terms of the number of times they visit the physician. The alternative hypothesis needs to include everything else. So that would say the population mean visits for the dog owners, when you then subtract the population mean visits for the control group, is something other than 0. There is a difference between those two populations. As you know, we will proceed as though the null hypothesis is true. And in step 2, we're going to create a distribution of all possible differences between sample means, and then we will mark off how much evidence we need to reject that initial assumption that the null hypothesis is true. Let's take note of a few things, and then we'll change views and we'll work on that distribution. In order to mark off those critical regions, I know that we're going to need to compute degrees of freedom. And degrees of freedom is based on the sample sizes. So the dog owners have 2, 4, 5 people in that group, and the control group has 2, 4, 6, 7 people in that group. Let's keep that in mind. At step 2, we need to create a distribution of differences between sample means, x bars. And like I just mentioned, we're going to create that distribution based on the idea that the null hypothesis is true. Well, when we plot those differences between sample means, if indeed the null hypothesis is true, right there in the middle, we should find lots of differences between sample means that are equal to 0. Eventually, we will compute a difference between our two sample means. And we need to figure out where is that difference in this entire distribution. And in order to figure out exactly where it is, we will transform that difference into a t-value. So we're going to mark off t-values down here as well. And we know right in the middle, we would have a t-value of 0. Of course, the real reason we're here right now is to figure out where are those critical regions. We discussed previously that we can figure out the critical regions by knowing degrees of freedom. And degrees of freedom is based on sample size. We can take the number of people in the first group, add the number of people in the second group, and then subtract 2 to find the overall degrees of freedom. In this case, we had 5 people in one group and 7 people in the other group. 5 and 7 equals 12, minus 2 equals 10. So we have 10 degrees of freedom overall. Let's consult our t-table and figure out what those critical values are. Here is our t-distribution. We, for this example, are doing a two-tailed test, and we're using an alpha of 0.01. We have 10 degrees of freedom. Degrees of freedom are listed right here. So I scroll down a little bit, and right here is the row for 10 degrees of freedom. As I move all the way down here to the right, so that I'm right underneath this column for an alpha of 0.01 two-tailed, I can see the critical value listed is 3.169. So my critical regions are marked off at positive and negative 3.169. 3.169 on the positive side and negative 3.169 on the negative side. Okay, now we know how much evidence we need to reject the null hypothesis. What we need to do next is figure out how much evidence do we have. In order to figure out how much evidence we have at step 3, we're going to have to take the difference between our two sample means and transform that into a t-value. But I don't even know the value of the sample means yet, so we're going to need to do a few computations first. And keep this in mind too. We're usually given information about means and sum of squares. We might as well compute sum of squares as well because we're going to need that to compute pooled variance. So I gave myself some room over here to do some basic descriptive statistics. Let's walk through that together and verify that the numbers I have are correct. Let's work on the first group first, and the first group was a group of dog owners. Let's first compute the mean. So we need to know the sum of x. So I'm going to take 8 and then add 5, 9, 4, and 6. The sum of x equals 32. I've got 1, 2, 3, 4, 5 people, so we can find the mean by taking 32 and dividing by 5. So it looks like the dog owners, on average, visited their physician 6.4 times during the period of this study. Of course, there's some variability in that data. Let's compute sum of squares because sum of squares measures the basis of variability. According to this formula, we need to know the sum of x, which we already know, but we also need to know the sum of x squared. So I'm going to take every single one of these values, square them, and then add them up. So let's start with 8. 8 squared is 64. We're going to add that to 5 squared. 5 squared is 25. 9 squared is 81. 4 squared is 16. 6 squared is 36. When we add all that up, that equals 222. So we start with the sum of x squared, which is 222, and then we need to subtract this fraction. Let's work on that fraction. According to the formula, we need to take the sum of x, square that value, and then divide by n. The sum of x is equal to 32. We computed that right there. So let's take 32 and hit the square key. That equals 1024. And now I need to divide that by n. So I'm going to divide it by, remember we have 5 people in that group, 5. That equals 204.8. 222 minus 204.8 equals 17.2. So that's sum of squares for the dog owner group. Let's do the same thing. Let's compute the mean and sum of squares for the control group. Let's first compute the mean. We'll verify my work down here. So let's compute the sum of x. Let's just add up all the scores. 10 plus 12 plus 6 plus 9 plus 15, 12, and then finally plus 14. The sum of x equals 78. Let's compute the mean. It's simply the sum of x divided by n. So let's divide that by 2, 4, 6. There are 7 people in that group. 78 divided by 7 equals about 11.14. So the control group visited their physician about 11.14 times during the study period. We need to compute sum of squares for that group as well. When we look at the formula for sum of squares, we can see that we need the sum of x, which we already have, but we also need the sum of x squared. So let's take every single one of these values, square them, and then add them up. 10 squared is 100. To that, we're going to add 12 squared is 144, so we'll add 144, plus 6 squared is 36, plus 9 squared is 81, plus 15 squared is 225, plus 12 squared is 144, plus 14 squared is 196, equals 926. So now we know the sum of x squared. Now we have everything that we need to compute sum of squares. Let's go ahead and compute it. The formula starts out with the sum of x squared, 926. We need to subtract that fraction right there. So let's work on the fraction. We need to take the sum of x and square it. We computed the sum of x right here when we computed the mean. It equals 78. So I'm going to take 78 and square it. Now I need to divide that by n. And remember, n equals 2, 4, 6, 7. So let's divide by 7. That fraction equals 869.14. When we take 926 and subtract 869.14, we get 56.86. That, my friends, is our measurement of sum of squares. That's the basis for measuring variability for that group. That was a lot of work, but it wasn't hard work. So don't get freaked out when you look at an example and you see the raw data. Computing a mean and computing sum of squares is not difficult. Once we get that, now we can move on to step 3, and we can figure out how much evidence we actually have. I mentioned to you that some students get stuck over here, and they just don't know where to start. You should always ask yourself, what do I need and what do I have? I need to know the value for these two means. We know that, we just computed it. I need to know this value right here. Well, remember, this is always based on the null hypothesis. And the null hypothesis states that the difference between these two population means is 0. So you can just go ahead and cross that out. That always equals 0. We also need to know standard error, the standard error of the difference between the two sample means. We don't know that yet, so let's look at a formula for that. Here's a formula right here. We need to know n in order to compute it. We know n for each group. We also need to know pooled variance, and we don't have that. So let's look at a formula for pooled variance. In order to compute pooled variance, we need to know sum of squares for each group, which we have, and we need to know degrees of freedom for each group, and we can easily figure that out just simply based on the number of people in each group. So we have all this information. That's where we should start. We'll take the sum of squares for that first group. We just computed it, 17.2. Add to that the sum of squares from the second group, which we just computed, 56.86. Degrees of freedom for the first group. Remember, this first group has 5 people, so they have 4 degrees of freedom. The second group has 7 people, so they have 6 degrees of freedom. So in the end, we have 74.06 divided by 10. Pooled variance in this case equals 7.41. Once we know pooled variance, we can stick it into this formula to compute standard error. Be careful when you're computing standard error. I've mentioned to you before that I think it's easiest to compute each fraction, add them up, and then take the square root. The reason why I think that's the smartest thing to do is because you can't add fractions when they don't have common denominators. And in this situation, the two groups have different sample sizes, so these two fractions do not have common denominators. We don't need to worry about that. We don't need to add any fractions. We're just going to compute the value of the fraction, find it, and then add it to the value of the second fraction. Let's walk through that together. All right, first of all, we know that pooled variance equals 7.41. So in this formula, we know the numerator right here and the numerator right here equals 7.41. For that first group, we had 5 people. For the second group, we had 7 people. So this is how we would structure the equation. Let's focus on that first fraction. Let's take 7.41 and divide that by 5. That equals approximately 1.48. All right, so we've got 1.48 right here. Let's look at the second fraction. Again, let's take 7.41, but this time we'll divide it by 7. That equals about 1.06, so we have that value right there. Let's add up those values and then compute the square root. So we have 1.48 plus 1.06 equals 2.54. And we need the square root of that, so I'll hit my square root key. That equals 1.59. Now that we know the value of the estimated standard error of the differences between the means, we can compute our t-statistic. We're going to look to see how big are the differences we actually see, and we're going to divide by the differences we would expect just due to sampling error. So we take that first mean, 6.4, and we're going to subtract the second mean, 11.14. That's a difference of nearly 5 visits to the position. We divide by 1.59, which is the standard error of the mean. Let's just confirm that calculation. We'll take 4.74, we can make that negative, and then divide by 1.59. That ultimately now gives us a t-value of negative 2.98. So there was a difference of nearly 5 visits to the position between those two groups, and that transformed into a t-value of negative 2.98. Now we need to figure out where is that value in the distribution of differences between means. Here is that distribution. We have a t-value of negative 2.98. Right here is a t-value of 0. Right here is a t-value marking off our critical region at negative 3.169. Our value of negative 2.98, it doesn't reach this point. Negative 2.98 is somewhere right around that area. That's where our difference between our two sample means is located. Of course, we need to ask ourselves that one critical question. Are we in the critical region? Are we in the rejection zone? And the answer is no, we're not. If we are not in the rejection zone, we should answer no to the remaining follow-up questions. Let's switch the views and then go through those questions. We found that this value was not in the rejection zone. Should we reject our null hypothesis? No, we shouldn't. We're going to continue to embrace that null hypothesis. What does that null hypothesis state? It states that the difference between those two populations is 0. In other words, they're the same. There are no differences. Well, somebody might say, how can you say that? How can you come to that conclusion? The people who have dogs visited the doctor only about 6 times. The people without dogs visited about 11 times. That's nearly twice as many. How can you say there are no differences? And we would need to explain that particularly when you have a sample size so small, those are the differences we would expect to find just due to sampling error. We have not effectively ruled out sampling error as a viable explanation for our results. So we said no, we are not going to reject the null hypothesis. Next follow-up question. Do we have statistically significant results? No, we don't. We do not have statistically significant results. Is it possible that we're making a type 1 error? No, it's not at all possible that we're making a type 1 error. The only time you can make a type 1 error is when you reject the null hypothesis. Then it's possible that you've rejected the null hypothesis incorrectly. That's impossible in this situation. Well, let's be fair. Let's just ask another question that obviously is on your mind. Is it possible that we're making a type 2 error? Yes, it is possible that we're making a type 2 error. And you might recall I told you that the examples we do in class, particularly the ones we do by hand, like this one, always have relatively small sample sizes. Otherwise, we'd be here crunching through the numbers all day long. If they have small sample sizes, that typically means they are underpowered research studies. And underpowered research studies are likely to result in type 2 errors. There might really be differences that we are not able to find. So is it possible that there really are differences between these two populations? Yes, it's possible. Is it possible that we're making a type 2 error? Yes, it's possible. So in your mind, make sure you can tease apart the difference between type 1 and type 2 errors. Of course, then we would interpret our results. We would fail to reject the null hypothesis. We would conclude that there's insufficient evidence to conclude that the pet owners differ from others in terms of the number of times they visit the doctor. In other words, there are no differences between the two groups. And then you'd see over here, we would summarize those results by saying we did a t-test with 10 degrees of freedom. The value that we computed was negative 2.98, and the probability of finding those results just by chance was greater than 1% based on a two-tailed test. Let's just remind ourselves why we decided to put p greater than 0.01. Remember, the difference between our sample means is right there. It's located somewhere within this big region. It's not located within that small rejection zone. It's in a big region. If I have to pick between the probability, p, of finding our results just by chance being greater than 1%, or the probability, p, of finding our results just by chance being less than 1%, I should pick the one that's associated with a big area, a big probability. Well, what's big? A probability greater than 1% or a probability less than 1%? Of course, a probability greater than 1%. And that's why we pick it, because area equals probability. At step 4, we also need to compute Cohen's d, a measurement of effect size. We usually feel better about computing that measurement of effect size when we have a statistically significant result, because once we find out that the results are statistically significant, we want to know how big is the effect. Here, although we measured a difference, although we measured an effect, it's not statistically significant. So in this case, although we can compute Cohen's d, we just don't tend to make a big deal about it. You can see in this situation, Cohen's d is a relatively large value. Look at it. It represents a difference of nearly 2 standard deviations between those two groups. So really, I was kind of unfair when I said we don't make a big deal about it. I'm still really interested in that Cohen's d value, because that's reminding me that I actually detected a large effect. It's possible that that effect that I detected is simply due to sampling error, and that is my conclusion right now. But it's also possible that this study was so underpowered that I just didn't have enough data to establish that effect. What researchers say to themselves in this situation is, maybe I should rerun this study. Maybe I should rerun this study, but this time collect much more data. Because it's possible there really is an effect there, and I need sufficient evidence to prove that. In all situations, it's always better to have more data. It's always better to collect more data, because we come closer and closer to measuring the entire population. We come closer and closer to the truth. Of course, we could follow up those 4 steps with a confidence interval. Because we used an alpha of 0.01 during those 4 steps, we would use a 99% confidence interval in this situation. We would construct that 99% confidence interval around the difference that we found between those two sample means. Remember, on average, the people with pets visited the doctor about 4.74 times fewer than the people without pets. When you plug in all the appropriate numbers, we find a confidence interval that ranges from about negative 9.78 to 0.3. Do you see how 0 is indeed included within that range? So you should be able to look at this confidence interval right here and know that we do not have statistically significant results. You should be able to look at that confidence interval right there and know that we failed to reject the null hypothesis. That's one thing that makes these confidence intervals really so useful. Because what we're saying with this confidence interval is that the true difference in the number of visits between these two populations is somewhere between about negative 9.78 visits and positive 0.3 visits. In other words, based on the data that we have right now, we could not rule out that the true difference in the number of visits is 0. So be sure you take some time to go through this video and compare your work to mine, and be sure you understand every calculation that you made. That wraps up our discussion of the independent samples t-test. You know, there are so many research studies out there that compare two groups that the independent samples t-test is used incredibly often. It's a great skill that you now have. Well, that's it for now. I'll see you in the next video. In the meantime, be safe.